I'm Treejunt, and you are watching Visuallab. In Lecture 2, we took a brief look at process memory and the four main regions. And in Lecture 4, we focused on stack memory and stack frames. So this time, we move to the part that answers the hook. Memory that can survive the function that created it. Heap memory. You already know what the stack is. You already know what a stack frame is. And you already know the broader process memory picture. Now we narrow the focus to one region, the heap. This is where dynamic allocation lives. Memory requested while the program is already running. And the critical difference from the stack is this. Stack memory is tied to a function call. Heap memory is not. The object lives until you explicitly release it. That is the reason the heap exists. Let us come back to the same code you just saw in the hook. See this line. Malloc is the standard C function for requesting heap memory. It takes one argument, a size in bytes. Size of int asks the compiler, how many bytes does one int need on this target? On the system we are using, an x86-64 Linux system, that is 4 bytes. So this line is saying, give me 4 bytes on the heap. See this? The allocator created a block on the heap. This is where your 4 bytes live, right here in the user data cell. But look at what sits before it. These are the allocator's bookkeeping records. This cell is labeled prev_size. This one is the size field. Your code never writes to these directly. The allocator manages them so it can track which chunks are free, which are in use, and how large each one is. And see these trailing bytes. The allocator may give you a block slightly larger than the exact bytes you asked for because of alignment rules we will cover shortly. These extra bytes are inside your allocation, but your program data does not use them. Now look at what Malloc actually returned. CP. Malloc returned an address. That address is now stored in P. So P is a pointer, a variable that holds a memory address. And that address points to the first byte of the user data in the heap block we just saw. Be very precise here. P itself lives on the stack. The thing P points to lives on the heap. That distinction is the foundation of everything in this lecture. Now see this line. Star P equals 42. The star here is the dereference operator. To dereference a pointer means follow the address stored in the pointer, go to that location in memory, and work with what is there. See the bytes change. The integer 42, which is 0x2 in hex, is now stored in the heap block. And because this is a little endian system, the least significant byte is first. So 0x2 sits at the lowest address, then 30 bytes follow. That is 42, stored as a 4-byte integer at the exact address P holds. Now watch what happens here. The function returned. The stack frame is gone. The variable P is gone. But the heap block is still there. The value 42 is still there. Nobody touched it. Nobody released it. This is the answer. Heap memory has its own lifetime. It exists until you explicitly release it, or until the process ends. The function that created it can return, be called again, be gone completely. The heap block does not care. Now that is a power. But it is also a responsibility. Because if nobody releases that block, it stays allocated forever while the program runs. That is called a memory leak. We will come back to leaks. But first, let us understand who actually gives us these blocks. Now let us look at this middle layer. When your code calls Malloc, it does not talk directly to the operating system for every small request. It talks to the allocator. The allocator is a runtime component that manages a pool of heap memory. It tracks which blocks are free, which are in use, and satisfies your request from that pool. When you request memory, the allocator finds a suitable free block, marks it used, and returns its address. When you release memory, the allocator marks that block free again. Now see when the allocator itself needs more memory from the operating system. When the pool is exhausted, the allocator asks the OS for more virtual address space. On Linux systems, you may see references to brk or mmap. Those are the system calls used. But your code never calls them directly. Your code calls malloc. The allocator handles the rest. The layering matters because it tells you where bookkeeping lies. The prev_size and size field cells we showed earlier, those exist for the allocator, so it can navigate the heap and manage free blocks correctly. Your program data sits inside the chunk the allocator defines. Look at the malloc signature. The argument type is size_t. Size_t is an unsigned integer type, guaranteed wide enough to hold the size of any object on this system. You use sizeOfInt instead of writing the literal 4. The C standard does not promise that int is 4 bytes everywhere. Sizeof asks the compiler, on this target, for this type, how many bytes? That one habit makes the code correct on every conforming system. Now the return type. Malloc returns void star. Void star means a pointer to memory of unspecified type. Malloc hands you raw bytes at an address. It has no idea what you intend to store there. That decision belongs to your code. In C, a void star assigns to any object pointer without a cast. In C++, you need an explicit cast, or better, just use new. Now see this check. Malloc can fail. If the allocator cannot satisfy the request, out of memory, invalid size, it returns null. Null is the null pointer constant. It does not point to any valid object. If you dereference it, the behavior is undefined. On most systems, you get a segmentation fault immediately. That is actually the better outcome. At least the crash is obvious. Silent corruption from other undefined behavior bugs is far harder to find. So the check belongs here. Always. Now look at this code. A complete example, malloc, a null check, and a write. This line asks the allocator for 4 bytes on the heap. Malloc found a free block, marked it used, and returned its address. That is now stored in P. But malloc did not touch the bytes inside that block. They contain whatever happened to be in that memory region before. Could be zeros. Could be garbage from a previous allocation. Could be anything. This is called uninitialized memory. Reading it before writing to it is undefined behavior. The bytes look real. The address is valid. But the content has no meaning your program gave it. Only after this line executes does the memory hold meaningful program data. See the bytes change. 42, 0x2 in hex is now stored at the address P holds. Allocate, then initialize, always in that order. Never read from an allocated block until your code has written to it first. Now see array allocation. 5 integers, each 4 bytes, 20 bytes total. Malloc gives back a single raw block of 20 bytes, nothing more. See this block, just bytes, no elements, no indexes. The allocator knows nothing about it. But ARR is declared as int star. That type declaration is what gives the block structure. The compiler now knows each element is sizeOfInt, 4 bytes wide. So ARR, I, is pointer arithmetic, base address plus I times 4. ARR 0 is the first 4 bytes. ARR 1 is the next 4, and so on. The single block becomes an array purely because of the pointer type. And see what ARR 5 would be, 1 element past the end. The address arithmetic produces a value, but you are touching bytes past your block. The compiler will not stop you. That is undefined behavior. One more detail. N times size event can overflow if n is very large. The result wraps around to a tiny value. Malloc gets that tiny size. Your code believes it has a huge block. That is a real class of vulnerability. On most 64-bit systems with reasonable values, it is not a problem, but the awareness belongs here. Now look at this example. This is a point struct, two integer members, x and y, for bytes each. When you allocate a point on the heap, Malloc gives you a raw 8-byte block. X occupies the first 4 bytes. Y occupies the next 4, laid out contiguously, just like the array. Now the arrow operator. pt arrow x means follow the pointer pt to the struct on the heap, then access member x. It is exactly the same as star pt in parentheses .x, dereference first, then member access. pt arrow x equals 10, writes 10 into the first 4 bytes. pt arrow y equals 20, writes 20 into the next 4 bytes. This pattern will appear constantly in the next lecture. Linked list nodes are heap allocated structs. Every time you write node arrow next, that is this exact operator. Now look at this example. This is Malloc. 1 block, 20 bytes. The content is whatever was in that memory before. Garbage, undefined. You must write before you read. Now this is calloc. 2 arguments, count and size. Same block, same 20 bytes. But calloc is Malloc plus 1 extra step. It zeros every byte before returning. So if you read an element before writing it, you get 0 instead of garbage. Calloc also performs the count times size multiplication internally and checks for overflow, one less thing to worry about. If you are going to write every element immediately anyway, Malloc is fine. You are zeroing memory you are about to overwrite. Both blocks are released with free. Calloc and Malloc allocations are freed the same way. Now look at this example. 3 integers, 10, 20, 30, allocated and initialized. Now see, realloc. We are asking for a bigger block, 6 integers instead of 3. Watch what the allocator can do. Option A, free memory, is directly adjacent. The allocator grows the block in place. Same address. Old data preserved. 3 new cells available at the end. Option B, no room to grow in place. The allocator creates a brand new block, copies your data, 10, 20, 30, into it, releases the old block, and returns the new address. Either way, if realloc succeeds, your original values are preserved. But the 3 new cells are uninitialized, right before you read. Now see why we used temp and not ARR directly. If realloc returned null, and we wrote ARR equals realloc ARR, ARR is now null. The original allocation is still alive, still using memory, but we have no pointer to it anymore. That is a memory leak created in one line while trying to resize. So store the result in a temp, check for null, then update your main pointer. One special behavior, realloc of null with a positive size, behaves exactly like Malloc. Useful in growth patterns where your pointer starts as null. Now see the other half of the model. This example allocates 4 bytes, stores 42, then frees the block and sets p to null. Free of p tells the allocator, this block is no longer mine. The block is returned to the allocator. But p still holds the old address. The pointer was not cleared. The block no longer belongs to your program. The allocator may hand it to the next Malloc immediately. Another allocation gets that exact block and writes new data there. The old value 42 is gone, overwritten, with no warning. If your code still holds p and reads through it, it gets whatever the new occupant put there, or crashes, or corrupts something else. After free, that pointer is invalid. Full stop. One defensive habit, set the pointer to null after freeing. This does not repair the heap. It does not protect other pointers to the same block. But if this variable is accidentally used again, you get a null dereference, which crashes immediately and obviously. Better than silent corruption. Now look at this example. P gets 4 bytes. 42 is written. Q is assigned the same address as P. Then the block is freed through P. Then line 8 tries to write through Q after the block was already freed. This pointer is called a dangling pointer. Its target has already been deallocated. And this access pattern is called useAfterFree. UseAfterFree is undefined behavior. The outcome depends on the allocator, the timing, the platform. The program may crash. It may silently corrupt other data and fail somewhere completely unrelated. Or it may appear to work until the memory happens to get reused differently. That unpredictability is what makes this dangerous. It does not reliably fail. It sometimes passes tests and ships to production. And see this, setting P to null did not help Q. Both variables held the same address. Freeing through P and nulling P leaves Q still pointing at freed memory. Dangling pointers survive wherever any copy of the address still exists. Now look at this example. P gets 4 bytes, 42 is written, then free is called twice on the same pointer, freeing the same block twice. The first free updates the allocator's bookkeeping, prev_size, and size field correctly. The second free sees a block it thinks is already free and updates records again. Now the metadata is corrupted. The next allocation could return an address that overlaps with a live object. Two parts of the program now believe they own the same memory. Double free vulnerabilities have been exploited to gain arbitrary code execution in real systems. One useful rule: free of null is valid in C and does nothing. That is why the defensive pattern works. Set to null after freeing. Then a second free is harmless. It does not protect aliases, but it is a clean habit worth building. Now look at this example. Process allocates 4 bytes, writes 42, uses the memory, then returns no free anywhere. It never frees. Every call to this function leaks one allocation. 10,000 calls, 10,000 blocks, all unreachable, all holding memory the program can never use again. The process never crashes from a leak immediately. But the heap grows without bound. Eventually the system runs out of memory, the OS kills the process, or the machine slows under swap pressure. In short-lived programs, this matters less. The OS reclaims everything on exit. In long-running servers, daemons, and embedded systems, a leak is a slow-motion failure. The fix is simple. Every allocation has exactly one release. The hard part is making sure that holds across all code paths, including error paths and early returns. Now see a different problem. Even with perfect discipline, every malloc matched, every free called exactly once, the heap can still become inefficient. See this heap. 2 free chunks, 32 bytes each, 64 bytes total free. Now malloc of 40 bytes comes in. On glibc that needs a 64-byte chunk, 16 bytes of header plus 40 of user data, rounded up to the next multiple of 16. 64 bytes are free in total, exactly what the request needs, but they are split across 2 separate 32-byte chunks. The allocator needs 64 contiguous bytes. Each free chunk is only 32. It cannot merge them. So the request fails, even though there is technically enough total free space. This is external fragmentation. Free memory exists, but is scattered into pieces too small for any large request. Now see internal fragmentation. You requested 5 bytes. On x86-64 with glibc, chunk_size equals roundup of 16 plus 5 equals 32. 5 bytes, your user data, the memory you actually use. 11 bytes, padding, added so the next chunk starts at a 16-byte aligned address. These 11 bytes are inside your chunk, counted as allocated. Your program never uses them. The allocator cannot give them to anyone else. If a new request comes in needing exactly 11 bytes, the allocator cannot offer this padding. It must find a fresh free chunk. This is internal fragmentation, free memory, locked inside existing chunks, invisible to the allocator, unusable for new requests. Now look at this example. Function f has a local integer x and a pointer p that points to a heap allocation. Cx, a local variable, lives in the stack frame for f. Cp, also on the stack, but p holds an address that points into the heap chunk. F returns stack frame gone, x gone, p gone. But the 32-byte heap chunk is still there, allocated, unreachable, leaked. Use the stack when the object is local, modest in size, and its lifetime ends when the function returns. Use the heap when the object must outlive the function, when size is only known at runtime, when it needs to be shared, or when it is too large for the stack. Stack is automatic. The compiler manages it. Heap is manual. You manage it. Stack is fast. Heap is flexible. Now move to C++. This example shows new and delete C++ heap allocation, including the array form and a class type. See new int of 42. Two things happen. Storage is obtained and 42 is immediately written into it. Malloc gives raw, uninitialized bytes. New gives an initialized object. For class types, Malloc never calls the constructor. New always does. The object starts in a defined state. Malloc returns null on failure. New throws std bad alloc by default. Use new with std nothrow for nulptr instead. For class types, delete does two things, calls the destructor first, then releases the chunk. Free only releases bytes. It never calls a destructor. Using free on a C++ object skips all cleanup. And delete of nulptr is valid and does nothing, same as free of null. For arrays, new with brackets must be matched with delete with brackets. Not delete, not free, delete with brackets. Mismatching is undefined behavior. For class types, delete on a new bracket array may only call one destructor, leaving the rest partially destroyed. Match them correctly, always. Now we arrive at the idea that ties the entire lecture together. Ownership. For every allocation, ask this: who is responsible for freeing this memory? When the answer is clear, one owner, one release. Heap management is tractable. When the answer is unclear, several parts hold pointers, nobody knows who frees. You get leaks, dangling pointers, or double free. Manual heap management is hard not because the API is complex. Malloc and free are just two functions. It is hard because ownership must stay correct across function boundaries, across error paths, across every early return. That is why C++ introduced ownership abstractions. Unique pointer gives the allocation exactly one owner. When that owner goes out of scope, delete is called automatically. You cannot forget. You cannot copy a unique pointer. You can only move it. Ownership transfers, one owner at a time. Shared pointer allows multiple owners. It keeps a reference count. Every copy increments the count. Every destruction decrements it. When the count reaches 0, delete is called automatically. Both are wrappers. Underneath, the same heap chunk, the same new and delete. But ownership is now tracked automatically. std vector and std string own their internal buffers. They allocate, grow, and free automatically. This pattern has a name, RAII. Resource acquisition is initialization. Acquire the resource in the constructor. Release it in the destructor. The destructor runs automatically when the object goes out of scope. The resource is always released. The language enforces it. I am teaching the manual model first for one reason. If you do not understand what malloc, free, leaks, and dangling pointers are doing underneath, RAII looks like magic. Once the manual model is clear, these abstractions stop being magic. They become exactly what they are, discipline tools, built to prevent the bugs we just studied. That is the heap. Let me tell you exactly what we covered in this lecture. What the heap is, a region of memory whose lifetime your code controls, not the compiler. How the allocator works, the middle layer between your code and the operating system. How it tracks chunks using metadata, how it rounds sizes up for alignment. The four functions, malloc, calloc, realloc, and free. What each one does, what it returns, and where it can go wrong. Uninitialized memory. Why malloc gives you garbage bytes and why reading before writing is undefined behavior. Arrays on the heap. How pointer arithmetic turns a raw block into indexed elements, and why going out of bounds is silent and dangerous. Structs on the heap. The arrow operator. How members are laid out in memory, the difference between the pointer and what it points to. The 5 bugs. Memory leak, dangling pointer, use after free, double free, and fragmentation. Where each one comes from and why each one is dangerous. Stack versus heap, when to use each one, what automatic lifetime means, and what happens when a function returns while heap allocations survive. And ownership, the one question that determines whether your heap management is correct. Who owns this memory? Who may use it? When does its lifetime end? I want to be honest with you about something. Most people learn C and never really understand what is happening underneath. They learn the syntax. They learn the rules. But the mental model is fuzzy. If you followed this lecture carefully, if you understood why the chunk is 32 bytes when you asked for 4, why the pointer lives on the stack while the data lives on the heap, why use after free sometimes crashes and sometimes silently corrupts, you are already thinking at a level most programmers never reach. That is not flattery. That is the reality of how few people actually understand memory at this depth. Now, what is next? The next lecture is linked lists, specifically the anatomy of a linked list node. A linked list node is a heap allocated struct with 2 members, a value and a pointer to the next node. That is it. That is the entire structure. But understanding it completely, understanding the layout in memory, the pointer chain, the ownership of each node, the lifetime, requires exactly the model you just built. Without this lecture, linked lists are a diagram you memorize. With this lecture, they are a memory structure you can reason about from first principles. See you in the next one.